Hello everyone, welcome to my channel. This is my very first vlog, so if you have any suggestions on my presentations, please feel free to leave me comments and I will try to improve in the future. So today I'm going to walk you through the very famous computer vision starting project, which is the dogs versus cats classifier. And the reason I'm doing this video is because I found there is no video that explains the transfer learning technology on this project. Although there are so many videos about this project exist already. And personally, I think transfer learning is a very strong tool that allows you to build models upon the already existed strong classifier to reach a very high classification accuracy. And in this video, I am going to illustrate the procedure of building a strong classifier on the basis of VGG16. Firstly, let me introduce you what VGG16 is. I suggest you to go through the paper I'm showing you right now, which provides more details about this architecture. Basically, VGG16 is an architecture of a very deep convolutional network for large-scale image recognition. It is developed by the winners from ImageNet Challenge in 2014, which gives a very high prediction accuracy for image classification tasks. The data source can be found from the Kaggle computation of Dogs vs. Cats website. And my code is developed on the basis of the notebook created by Zihua Noor. Now let's go through the code together. In the first step, we extract the zip files provided and rearrange them into the following subfolders structures. After we have this path, we could use the Python built-in function of image data generator to generate the train test and validation batches with preprocessing function. And after we have the data structure of the train test and validation batches, we could proceed to future steps. For example, visualizing training images and use them as input for training, testing, and validating models. Now let's move on to the step where we create models using manually defined layers, and you could use the model.summary to display the model structure and compile. We train the model using model.fit. And you could see from the output, our training accuracy continues improving, but the validation accuracy does not improve a lot. This is an indication of overfitting. It is more straightforward if we plot the training and the validation curve. You could see the from the loss curve and accuracy curve, the validation loss and validation accuracy did not decrease or increase together with the training loss and accuracy. Now let's move on to the prediction using the developed model. We could see there was overfitting before, so let's try it on the test dataset and plot the confusion matrix to see how the model works on test data. And this section is the display of the test images, of portion of test images and test label. We use model.predict to predict the labels for test batch. And plot the confusion matrix. We could see that a high proportion of data are misclassified. Let's move on to the fine-tuning part, where VGG16 model actually comes in. We could use the VGG16 model from the TensorFlow Keras library, and this is a summary of the model architecture. So what we do here is to create a sequential model and recursively adding the layers from VGG16 model except from its very last layer. And we fixed all the training parameters of the architecture to be unchangeable, and adding our very last custom layer, so that we only update the weights of the last layer, which maps the architecture into our final class predictions. This is a model summary, and we compile our model. This is a callback I personally added to stop training when the validation loss does not decrease anymore. We train using model.fit again, and we predict on our test data after implementing and training this VGG16 model, and plot the confusion matrix. As we could see, the results showing the model is not overfitting anymore and have much better prediction result comparing to the previous model. And lastly, we could try predicting on some actual test data given. In this piece of code, I extracted 10 test data from the test dataset given, and I applied model.predict for the newly generated test batch. And I used this piece of code to display some test pictures as well as their predicted classes. In this figure, 1 represents a dog, 0 represents a cat, and we could see that all of them are predicted correctly. Finally, we could save our model by using model.save for future use. Next, I'm going to show you a very interesting expansion of this project, which is a GUI that supports classifying a custom image uploaded by a user. Basically, is to load the model we saved before and detect the user specified file path to preprocess that image in this file path, and make the model to predict the image and display the output. I could show you the actual display of this GUI. We could upload a custom image. For example, I can choose from the test1 subfolder and classify image. So the result is correct. It was predicted by the model that it is a cat.